Hello, I hope you're doing well. Today we are going to talk about compound events and finding the probability of compound events. That word compound just means you have two or more events put together. So instead of just one thing happening, like a single roll of a dice or a single flip of a coin, maybe we're going to take this penny and flip it twice. Ooh. Or maybe we're going to spin the spinner and roll the dice. Ooh, or something like that. So think like compound words. You know how compound words like playground are two little words put together? Well, same idea with compound events. It's two simple events put together. So let's get that defined here. So compound events would be two or more events put together. And the way that you will put them together is you will find the probability of each event and multiply. Now, there are two types of compound events. We have independent events and we have dependent events. So let's look at those. What does it mean to be independent? I am independent. I'm an independent woman means I stand alone. I can stand by myself. Independent events. So for this, that means that the two events stand alone. The probability of one, what happens in one event, has no effect on what happens in the other event. Two events stand alone, which means the outcome of one event doesn't affect the probability of the other. So that would be like if I'm going to spin the spinner and then I'm going to roll this dice. Does what I get on the spinner have any bearing on what happens with this dice? No, that doesn't make sense at all. They're completely independent of each other. The dice isn't like, ooh, you were red. Ooh, I should be a 2. No, that's not a thing. So those are independent events. And that seems pretty obvious. But sometimes these can be tricky, actually. So let's look at dependent events. That would be the opposite thing. That means that the outcome of one event, I'll say of the first event, changes or affects the probability of the other event. So we'll talk about that in a minute. What would happen if I would flip this coin more than once? What if I flip it and I got heads? Well, what was the likelihood of me getting heads this time? It was 1 out of 2, right? Everyone knows that. What about this time? What's the likelihood I get heads again? Still 1 out of 2 because it's still a coin and it still has 2 sides. Was the second flip affected at all by the first one? No. So which type are these? These are independent events. Okay, so now that seems obvious, but you'd be surprised how many times people don't understand that. Do you ever feel like, let's say that I flipped this coin 4 times in a row and I have gotten heads every time. Oh my goodness, this next time, it has to be tails, doesn't it? No it doesn't, because this next flip is independent of the other one. It has no memory of what it did on the previous flips, so it's still only a probability of 1/2, whether it's going to be heads or tails. Oh, I got heads. So those are independent events. Kind of funny place where people mix this idea up is with having babies. I had an aunt and uncle. Ken and Peg, and they had, at the time, they had 5 kids, and they were all boys. Oh my goodness, can you imagine having 5 boys? Well, my Aunt Peg was expecting her 6th child, and I remember sitting around the dinner table and people saying, it's gotta be a girl this time. Oh, it has to be, for sure. What was the likelihood of that baby being a girl? It was still 1 out of 2. It was still 1/2, because those babies being born are independent events. So we tend to get confused about that sometimes, whether things are independent or dependent. So let me show you what a dependent event could be like. Let's say I have people in my classroom here, and I say, I'm going to choose 2 kids, and I'm going to choose them independently. And the first kid is going to be the president, and the second kid is going to be the vice president. And I want to know the probability that I get a girl both times. So let's say that my room has 10 kids, and there are 5 boys, 5 girls. So what's the likelihood I get a girl for my first pick? Now I'm just going to randomly pick, okay? So just like draw names from a hat, point to a list, something like that, something random. So there's 5 girls out of the 10 kids, so that would be a 5 out of 10 chance for the first girl. Here's how you'll see this written. I should be writing this. So I want to know so there are 10 kids in the class. 5 boys and 5 girls. And I want to know the probability that I get a girl for president and then another girl for vice president. So for that first girl, that would be 5 out of 10. Now, for the next girl, so let's say I say, Elena, you're president. So I choose a girl, she's president. How many kids are left sitting over here that are going, oh, please pick me for vice president? Now there's only 9 kids who are eligible. Do you see how there are less children? Because I already have one chosen and I can't choose her again. You can't have somebody, the same person, be president and vice president. That doesn't make sense. So this is an example of a dependent event because the second event's probability is changing. It's not going to be 5 out of 10 now. It's because I already have a girl chosen. So of those 9 kids that are left sitting in the room, how many of those 9 kids are girls? Now, I know there were 5 to begin with, but remember Elena, I already chose her. She's president. So there's only 4 girls left. So, oh no! Go back, go back. Where's that? There are only 4 girls left. So my numerator right here is going to be a 4. So we have, let me write that better. We have 5/10 times 4/9. And we can do some reducing here. I think I'm going to do that to make these numbers smaller. So 5 and 10 could reduce to 1 and 2. The 2 and the 4 could reduce to call it a 2 and a 1. So now if I multiply my numerators, I'm going to get a 2. 1 times 2 is 2. Multiply my denominators, 1 times 9 is 9. So the 2/9 chance of getting a girl for president and also a girl for vice president in this situation. So there is that. So this next page has an example that is going to be the basis for the puzzles that we'll do. So this jar contains 4 blue, 6 red, 5 orange, 3 yellow, 4 black, and 8 green marbles. Whew, that's a lot of marbles in there. I wonder how many marbles that is. So go ahead and add those up, see how many marbles you get. I think there's 30. Are there 30? Let's see, that would be 12 and another 12 and 6 makes 30. Yep, so we have 30 marbles. So I'm going to write that down here. 30 marbles. So for this first draw, I want to find the probability of getting a blue and then a yellow, and I'll explain the with replacement in just a second. So what's the likelihood I get a blue marble on the first draw. Well, how many blues are there? I want to know how many marbles are in that jar that would make me go, woohoo, I got a blue. Well, there are 4 of them. So that would be 4 out of 30. So the with replacement part means that I'm going to take that blue, or I'm going to pull out, woohoo, it's a blue. And with replacement means I'm putting it back. Okay, so I don't get to keep this blue marble. This is not mine forever. I have to put it back in the jar. So when I reach in to do my second draw, how many marbles are in that jar? Well, there's still 30 because I put that blue one back. So we're at 30 marbles still. And on this draw, I'm hoping for a yellow. Well, how many yellow marbles are in there would make me say, oh, woohoo, I got it. Well, if you look, there's 3 of them in there. So that would be a 3 up here. I think we can do some reducing with this. Would these be independent or dependent events, though? These are independent because the fact that I got a blue, said woohoo and put it back, didn't change what was going to happen with the yellow marble. If that first marble had been green and I put it back, or black and I put it back, it didn't matter. There were still going to be 3 out of the 30 yellow marbles in there for the second draw. So now let's go back to reducing. Let's see, I could reduce these by 3 and make it a 1 and a 10. I could reduce the 4 and the 10 by 2s and make it a 2 and a 5. I could reduce the 2 and the 30 and make it a 1 and a 15. I think that's everything. So my numerators, I have a 1 times 1, which is 1. And then my denominators, I have a 15 times 5, which is 75. Okay, so this next problem, I'm just changing the situation a teeny bit. Now, I'm going to reach in, draw out the blue marble, and then I get to keep it. It says without replacement for this problem. It means this is my blue marble. I am not putting it back. Okay, so to begin with, there are 4 blues in there out of the 30 marbles. But this time I draw a blue out and I keep it. How many marbles are left in the jar? They're not 30 anymore because the other one is mine. So now there's only 29 marbles left. Now on the second draw, what color are we hoping for? Yellow. Yeah, we're hoping for a yellow marble, and there are 3 of those. So we have a 3 up here. I think we can do some canceling because I see the 3 and the 30 would both be divisible by 3, so I could make it a 1 and a 10. The 4 and the 10, I could do some reducing by 2 by those and make it a 2 and a 5. So my numerators look like I have 2 times 1, which is 2. My denominators, I have 5 times 29. Oh goodness, 145. And there you go. So it does matter if it's an independent or dependent event because it's going to change your probability. So you're going to have to watch that. So I think that is everything. So remember that Jesus loves you, and so do I. So do your math.